Okay, welcome everybody. Thank you for showing up. Morning after the banquet. I know it's a tough time to make it. I feel badly for the presenters, but we're going to do a great job anyway. They know I like to keep to time, so we may as well begin. Jihan, second-year student, PhD student in the Department of Computer Science and Technology at Tsinghua University, supervised by Professor Dan Li, who we saw yesterday on the screen, and Dr. Li Chen. His research interests include data center networks and LLM systems. He's going to talk to us about ATOP. It's a really cool way of designing new topologies.
Okay. Hello, everyone. I'm Zihan Yan from Tsinghua University. Today, I'm going to talk about our work from ATOP to ZCube, automated topology optimization pipeline, and a highly cost-effective network topology for large model training. With the rapid growth of AI, model sizes have reached 100 billion or even 1 trillion parameters in the last 10 years. Training such models typically requires tens of thousands of GPUs, which in turn demands large-scale GPU clusters. So these GPUs are typically interconnected through data center networks, and the topology deeply impacts the performance, cost, and fault tolerance of GPU clusters. The first core metric is performance, which determines training iteration time, bandwidth, and latency. Communication can take up 35 to 50% of the total training time. The second metric is network hardware cost, which usually accounts for 15 to 20% of the total cluster cost. And the third metric is fault tolerance. About 10% of training errors are caused by network issues. Topology design is also not a one-time deal. There are at least 3 scenarios that necessitate design processes. The first is initial construction, where architects build a new cluster to meet specific needs. The second is incremental adjustment, such as recabling to reduce hardware cost. And the third is expansion, such as scaling a 1,000 GPU cluster to 4,000 GPUs. Beyond that, new model architectures and parallel strategies bring new traffic patterns, which impose new requirements on the topology. And the network hardware itself keeps evolving. The switch throughput has been doubling about every 2 years. And we are at 51.2 Tbps now. Manual design by human experts is the most common design approach, but it faces 3 problems. First, the design space for large-scale clusters is vast, lead to inefficient exploration. And then the experts may fear beautiful topologies and miss better designs. Finally, it's also hard to optimize multiple objectives. The benefit is that these topologies are reasonable. A naive way to automate topology design is to use an adjacency matrix representation, but that gives 2 to the 16,000 candidates for a 16,000 GPU cluster, which is an impractically large search space. Counter introduced a domain-specific language to simplify design, but it is still hard to express end-to-end performance goals and still relies on human experts, so it is not fully automated. Thus, we ask the question, can we combine human intuitions and automated exploration in cluster topology design with multiple objectives? To this end, we propose ATOP, an automated topology optimization pipeline. The first part of ATOP is topology modeling. We study all the popular DCN and HPC topologies and distill the expert intuitions behind each design. These intuitions reduce the search space by about 10 to the power of 1,600 times. And the second part of ATOP is topology optimizer. It allows users to customize their objectives and perform efficient optimization using the optimization algorithm in SGA2. As a stopping criterion, we use a number of generated topologies. And the third part is the topology evaluator. We efficiently evaluate topologies using a flow-level simulator, and we propose a two-stage evaluation method. In the first stage, we evaluate all generated topologies and their fragmented training workloads, which gives us about 5,000 Pareto-optimal topologies. And in the second stage, we use time-consuming end-to-end training simulation to evaluate the performance of these Pareto-optimal topologies. And we first evaluate the efficiency and scalability of ATOP. In stage 1, we consider 14 optimization objectives, including performance, cost, and fault tolerance. In stage 2, we evaluate using end-to-end GPT-3 training simulation. And for the stopping criterion, we used 100,000 generated topologies. Our testbed is a single server with 256 CPU cores. According to the results, ATOP can discover new superior topologies for a 16,000 GPU cluster within just 3 days. And each point in this figure represents a topology. We identify the Pareto frontier between performance and cost. And the topologies on this frontier are called Pareto-optimal topologies. We also discovered that well-known designs such as Real-Optimized Factory, Real-Only, and HPN from Alibaba Cloud are not Pareto-optimal. And we also evaluate that ATOP can support different design scenarios. The first scenario is building a new cluster with different specifications of switches and NICs. The second scenario is rewiring a 4,000 GPU real-optimized factory cluster, optimize the topology without adding more switches. And the third scenario is scaling up a 1,000 GPU cluster into 4,000 GPUs with fixed switch and NIC specifications. From the results, we find that cost-effective topologies share similar architectural features. So we summarize and define this type of topology as ZCube. So this is what ZCube looks like. The first feature of ZCube is that each GPU is equipped with a dual-port NIC. And the second feature is that the NIC ports are connected to different layers of switches. The third feature is that the switch layers are interconnected as a complete bipartite graph. These are the 3 core features of ZCube. This figure shows ZCube at large scale, built as a 16,000 GPU cluster using 51.2 TPPS switches. We can support up to about 590,000 GPUs at max, and we show more details in our paper. Next, we introduce the properties of ZCube. Firstly, it has a low diameter property. Any pair of GPUs can communicate within 2 hops in ZCube, whereas in HPN 7.0, it takes 3 hops. The advantages of the low diameter include, first, it can reduce GPU to GPU communication latency, which improves distributed training, especially pipeline parallelism, where many small flows are generated. And second, it helps mitigate conflicts in flow-level load balancing. And finally, shorter passes with fewer switches and links can lower the failure probability. ZCube also has a lower network cost. When building a 16,000 GPU cluster, ZCube can reduce the number of switches by 1/3 and reduce the optical module cost by 25%, which overall allows network hardware cost to be reduced by about 26 to 46%. And ZCube also provides strong fault tolerance. We show this through simulation and a single TOR failure. We evaluate the iteration time of GPT-3 training with and without failures, and the results show that ZCube suffer much smaller performance degradation. The dual-ponic and low-diameter features of ZCube ensure fault tolerance under single-tor fault. Other fault signals are detailed in our paper. Next, we evaluate ZCube using the iteration time of two models as metric. The evaluation is conducted with a packet-level simulator where we apply packet spring for load balancing. The baseline topologies and training setup are shown in these tables. The results show that compared to the state-of-the-art topologies, ZCube improves end-to-end model training by 3 to 7%, while reducing network hardware cost by 26 to 46%. And this speed up comes from ZCube's low diameter property, as pipeline parallelism flows and large-scale data parallelism flows typically require 3 to 5 hops in other topologies. But in ZCube, they need only 2 hops. We also build and test a real ZCube. The testbed consists of 4 NVIDIA GPU servers and 8 Mellanox switches. We evaluate it using NICO and NICO tests, and the metric is the bus bandwidth of all reduced and auto collective communication. The results show that ZCube matches RFT in both all reduced and auto performance, while reducing hardware cost by 25%. To summarize this work, we propose ATOP, an automated topology optimization pipeline that can discover superior network topologies for large-scale GPU clusters within a short time. And using ATOP, we discovered ZCube, a new topology with superior cost effectiveness, low network diameter, and strong fault tolerance. That's all. Thank you.
Wow, fantastic. Well ahead of time as well. Any questions from the audience? Tough crowd. Okay, I have 1 or 2 questions I'd like to ask. The first was admitting that I had a scan through. The first question is the edge density. I couldn't tell, is it worse or just similar to the topologies that you started with, where it's roughly the same number of edges, but they're connected in different ways? It was really hard to tell from thinking in my head.
Okay. That's a great question. And we first used the adjacency metric first, but we found that it will result a large-scale space, and we can't discover a superior topology in the short time. So we proposed ATOP, and we introduced a new topology modeling method, and based on the layered and symmetry structure to we can just using about 10s of the parameters to represent a topology, and this is also a union method, and we can use this method to represent the fat tree, B-cube, dragonfly, D-cell, and many other famous D-cell topologies in a same method. Yeah.
Okay. And I ask because if you've ever been in a data center, you know cabling can be a terrible mess, and so the people actually care about this in practice. It might be worth just trying to characterize so people can plan. It's really interesting. Second one, I know the world is about GPUs these days, but why not just regular data center topology? Like, are we suggesting that maybe we should do away with the ones that we know about and use, and we should start using ZCube?
And we are trying to deploy ZCube, and a new topology is not easy to be deployed, as almost every data center topology use the cloth or fat tree now. And so we want to deploy a new topology. Yeah.
All right. Any others from the audience? Then I'm going to take you out of your comfort zone. Last question. Okay.
Okay.
Could this be applied in other domains that are nothing to do with computers? So for example, and this will come up later in the session, I think, why not air travel? There's a set of people have this view that planes travel point to point as the crow flies, as we say, straight lines, and it's not true. There are waypoints that we set. Maybe we could choose the waypoints differently.
As ZCube is designed for GPU clusters, the scale-out network topology, and maybe it can also use in the traditional data center networks, and maybe it can also use in other domain. Yeah.
Okay, thank you very much. Please thank the speaker.